another week, another set of problems. Today we're looking at continuous probability distributions. So, video URL to follow, you'll see it on the usual playlist. So, let's start off with some good old true or false theory. Remember, this mostly is just to give you a little bit of extra theory. The format true and false is really not ideal. So there you have it. What do we got here? Well, a uniform distribution is a continuous probability distribution, which says the probability that x is in any two intervals of equal length is the same. Yes, that is a uniform distribution. That is the rectangular distribution. For a continuous distribution, P, the probability of x less than or equal to 100 is equal to the probability of x less than 100. You'll just notice the only real difference is this one has an equal sign and this one doesn't. And yeah, for a continuous distribution, it barely makes a difference if you have the equal to or not equal to. So that is true. A continuous probability distribution having a rectangular shape. Okay, so similar to number one, where the probability is evenly distributed over an interval of numbers is called a uniform probability distribution. Yep, that is correct. That's true. For a binomial probability experiment with n equal 150 and p equals 0.2, it is appropriate to use the normal approximation. Well, if you are going to use the normal approximation, you need to check and make sure that n times p is greater than 5 and that, looking at my formula sheet, n times 1 minus p has to be greater than or equal to 5. So you have to check. Well, let's see. So 150 times 0.2, is that greater than or equal to 5? Well, if you type that in on your calculator, you're going to get 30. So yeah, that works. Now for this check here, it's clear this one's going to work. 1 minus p is 0.8. Okay, so this one worked, this one's going to work as well. No need to even check. Answer's true. Keep in mind, if you're doing a long or short answer question, you actually need to show the work. Okay, but for a true or false or multiple choice, not necessary. Alright, a little bit more theory here. So which of the following statements is not, oh, I keep losing my pen. It's going to drive me mental. Okay, so is not a property of the normal probability distribution. So the normal distribution is symmetric. Yes. 95.44 of all possible observed values of the random variable x are within 3 standard deviations. Pretty sure it should be 2 standard deviations are within that 95-96 range. Right? That's that whole 68 95, 99 rule or whatever. So it seems like this is the one that's not true. However, I always like to check them all to make sure. So the mean, median, mode are equal. Yes, in the ideal distribution, that's true. The area under the normal curve to the right of the mean. Okay, so to the right of the mean, here's a normal distribution. The mean is here, so to the right of it is equal to the area under the normal curve to the left. Yes. When you have a perfect normal distribution, that is indeed true. And 68.28 of all possible observed values of the random variable x are within 1 standard deviation. Yes, that's true. That is true. 1 standard deviation of the mean, you get 68%. Yes, so this is definitely the answer. Number 6. The blank distribution would most likely be used to describe the distribution of time. Ooh, time between arrivals of customers. Yes, time between arrivals is exponential. If we're talking about average time, like over a certain period of time, then it's Poisson. If it's between those intervals, then it's exponential. That is tricky. Sneaky. Ooh, there's one more. When a blank probability distribution is used to approximate a blank probability distribution, we must make a blank correction. Perfect. Well, this definitely has something to do with the normal approximation. And so if you're sort of doing some elimination, global isn't a word we use, finite, finite. So it's pretty much between these two here. So when a continuous, let's try, when a continuous probability distribution is used to approximate a discrete probability distribution, we must make a continuity correction. Huh. Or is it a discrete probability distribution is used to make a continuous? Basically, this is definitely the normal approximation. So when we're doing the normal approximation, we are talking about, if you look at your formula sheet, I'll drag it over here a moment. Notice how this is under discrete random variables, right? Like the binomial distribution is a discrete probability distribution. So when you do the normal approximation to the binomial distribution, you're taking a discrete distribution and you're making it continuous. So it's going to be this answer here. So discrete, continuous, we make the continuity correction. That's that whole x plus or minus 0.5 thing from the notes. So cashier service time at a local bank has an exponential distribution with a mean time of 2.5 minutes. All right, so that's the mean time, 2.5 minutes. What is the probability that the service time is no more than 3 minutes? Okay, well, we're looking for probability that x is no more than 3 minutes. So less than or equal to 3. Well, and it's exponential. So grab your handy dandy formula sheet, boop, here it is, and you're checking out the exponential distribution here. So a couple things to note. You need to find this lambda character. That's this fancy looking character here. It's called lambda. So we do have a formula right down here for x less than or equal to a number, and it's 1 minus that e to the power of negative lambda times c. So that's the formula we're going to be using. And just note that the mean time is equal to 1 over lambda, and we need to find lambda. So what that means is we have some work ahead of us. So we know that the mean time is 1 over lambda. Now we need to find lambda. So just good old basic math. You can solve it for lambda. And look, this is not on the formula sheet, but you'll have to remember it if you're having issues with that. And the formula we're using is this one here. So before we can do it, we need lambda. So if you plug in the numbers, we know that the mean is 2.5. So that's lambda. You can type that in on your calculator. You type it in, you get 0.4. So there you go. After that, it just becomes a matter of popping it into the equation. Remember, this is c, so we're going to use that in the formula there. So we're going to go 1 minus e to the power of negative 0.4 times 3. So you can pop that in on your calculator. Just remember, this is the exponential distribution there, Euler's number. So you're looking for a button that looks like that on your calculator. So plugging it in on the calculator, just give me a moment here. So 1 minus e raised to the power of negative 0.4 times 3, and you're going to get 0.6988. And there it is. Very nice. Really easy to turn this into a short answer question. So it doesn't need to be multiple choice. All right, next. A car company is testing the fuel efficiency of mid-sized cars. Great. They established that fuel efficiency is normally distributed. So right away, as soon as I hear that, I'm like, okay. That's the formula for a z-score. With a mean of 32 and a standard deviation of 0.8. Amazing. What is the probability that the rating for a selected mid-sized car would be less than 33.2? All right, so we're looking for probability that x is less than 33.2. Perfecto. So we are going to use our z-score formula. And basically, we're going to be looking for the probability that z is less than whatever z-score we get out of this formula. So we're going to go ahead and calculate it out. Now, the x value we're using is 33.2. It's the one given in the question. Subtract the mean, 32, divided by the standard deviation of 0.8. very nice. And, oh, good, junk mail. Perfect. So, we're going to go 33.2, subtract 32 divided by 0.8. We get a z-score of 1.5. So, as I said before, we now know that we are looking for this probability that z is less than 1.5 up here. If you draw a nice, fancy-looking picture, like this, there's the mean, which has a z-score of 0, and, just approximately z-score of 1.5. Remember, this picture is just to help you figure it out. We're looking for, the magical, the probability, right? So it's less than 33.2, right? So here's x equals 33.2. Here's the mean at 32. And get the area. Oh my goodness, my email's going mental. I get a lot of junk email, apparently. So we're looking to the left of that. Now, when you bring up your z-scores, your z-score table, here it is, looking for 1.5. So 1.50, so 1.5, first column, so 0.9332. So we're going to write probability that x is less than 33.2 equals the probability that z is less than 1.5, and that is 0. What did we say? 9. I can't remember what we said. I'm trying to read all the freaking emails I'm getting. 93 to 93. 93.32. Oh, there we go. So 0.9332. That is part A. By the way, in case you didn't notice, the answers are down here upside down, just so you can check it yourself. And here we go. More than 33.2. Okay, so probability that x is greater than 33.2. Well, if we're looking for greater than, then we'd be looking for whatever corresponding z-score z is greater than something. Now, we found that z-score here, right? The work is going to be identical. The only difference is the direction we're looking. So because it's greater than, we'd be looking to the right of that value. So here's the mean of 32. Here's our value of 33.2. And instead of looking to the left, right, we're looking to the right because we're looking for greater than. Well, we know that z-score is already 1.5. Okay, so now we know that the probability that z is greater than 1.5 is going to equal 1 minus the probability that z is less than 1.5. So I am looking for you to write this, right? This is the logic of what you're doing. So we're going to go to the table. We already looked up the value. It's 0.9332. So we're just merely going to go 1 minus 0.9332. And can I do this in my head? Should I try? Yes, always try. There we go. I believe I got that right. So 0.0668. I'm going to see. That looks about right. Yep, perfect. There you go. That's a neat little question. You had a less than and you had a greater than, so it kind of covers most of the things that can happen to you. The other cases where you get in between two numbers. And oh my goodness, I have to pause the video to check my phone. What could this be? More junk email? All right, my friends, another question. So the distance between store outlets in a chain of stores in a large city is normally distributed. Great. Well, then you know that you're probably using this formula. With an average of 50 kilometers, okay, so that's the mean. It doesn't hurt to write the units. And a standard deviation of 5 kilometers. Yeah. Well. So, as promised, what's the probability? So what's the probability of finding a store between 50 and 60 kilometers? So that is smaller number first. So that's what we're asking. store between 50 and 60. Is it included? Is it not included? It really makes no difference for the normal distribution. You're taking a slice that's infinitesimally just a little bit bigger, which makes zero difference. So that's why, in general, we don't need to worry too much. Although we do try to keep these signs straight in the questions, just for, just because math matters. So always want to be as precise as possible. Now, between 50 and 60, it's unclear whether or not it's actually included. So yeah, I digress. So if we're going to do this, we're basically going to be finding two z values. And we're going to be subtracting the smaller one from the bigger one, basically, is how these questions work. So for one of them, we're going to be using the x value 50, and for the other one, we're going to be using the x value 60. So here we go. There's the formula. Let's go ahead and do, x equal 50 on this side. So z equals 50 minus the mean, which is 50, divided by standard deviation of 5. Well, if you're like me, you're going to realize that we got 0 divided by 5, which is just 0. So if you're drawing the normal distribution, you got the mean here at 50, which represents a z-score of 0, and the x value is also 50. We know from theory that when we look up the probability that z is less than 0, we're going to get 50%. All right, we're right at the mean. We're looking to the left, so we're finding this area here. Just in case you don't believe me, z equals 0.0. There it is, 50. Yeah. So, all good. Yeah. Well, there's that. Now we're going to do this one here. So, same formula. And what do we get? 60 minus 50 divided by 5. Well, this is another easy one to do in our head. 60 minus 50 gives us 10 divided by 5, which is 2. So that's great. You got this here with your mean at 50 and the x value at 60. And we are going to be looking for probability that z is less than 2, which would be this one right here, z equal 2, shading in this area here. So look it up on the table. Z equal 2.0, 9772. So 0.9772. There's that answer, there's that answer. Now, remember, if you're drawing the picture, which I think is very important to help you visualize, there's a normal distribution. X equals 60, x equals 50, z-score of 0 over here, and z-score of 2 over here. Now, we are looking for the probability that the average distance is between 50 and 60. So we're looking for this in between section. We're looking for this part of the normal curve. Now remember, what have we done? We found how far it is from here to here, right? And we've also found how far it is from here to here. So if we simply subtract the big arrow from, if we subtract the small arrow from the big arrow, you're going to be left with from here. Should I use a different color? You'll be left with from here to here, which is the area that you're looking for. So it is important to, write that out. So we can write probability that our x value is in between 50 and 60 equals probability that z is less than 2, right? That's the big number. Subtract probability that z is less than 0. So now plug in the numbers. So 0.9772 subtract 0.5 equals 0.4772. And there's the answer. Good job. Very nice. Next question. All right, we need to close that because that is There. Next question, my friends. A plant manager knows the number of boxes of supplies received weekly is normally distributed with a mean of 200, okay, and a standard deviation of 20. What percentage of the time will the number of boxes received weekly be between 180 and 210? Well, looks like another one of those questions where we are looking for an in-between. So if we draw our normal distribution, because they said it was normally distributed, and the mean is here at 200, and what are we looking for? So we're looking for between 180, so we're looking for the x value 180 and 210. So by no means does this need to be drawn to scale or anything, but we're looking for the in-between area, right? So I just really want to hammer this in here. So you're going to be able to find this curve. Thought I switched to green. You're going to be able to find this curve, right? So you'll be able to find the big green area, and then you'll be able to find, ooh, rainbow pen, you'll be able to find this curve here. Okay, so visually you can see, if you know the entire green piece, and then you subtract the rainbow piece, you will be left with this in-between piece. Okay, so that is the concept of finding between two values. So you got to do two calculations, get two z-scores, look them up, and subtract the small one from the big one is always how it works. I don't want you to reduce it to that, like that's what you end up doing, but the reason why is demonstrated by the diagram. So let's go ahead and figure out some values. So we'll go ahead and do, the x value of 180, and over here, hopefully with enough room, we'll do the x value of 210, and we'll write out our question. We're looking for probability that it's between those two numbers, and it's going to be equal to probability of z less than some number subtract probability of z less than the other number. So we'll fill it in as we go. Yay! So x is 180, subtract the mean of 200 divided by the standard deviation of 20. So that's going to give us negative 20 in the numerator, I do believe. So you're going to get a z-score of negative 1. Well, let's go ahead and look up the probability that z is less than negative 1. So we're doing the rainbow section. I'll even change to my rainbow pen. So let's go bring up the z table. Z equals, it is negative 0.1. So 0.1587 right there. So 0.1587, a wonder bar. Let's go ahead and pop in the negative 1 here. Actually, my bad, because this is likely going to be the smaller number, right? How do I know that? Well, because I just did x equal 180. 210 is going to be bigger, so it's always the big number minus the small number. So small number is going to be over here, so right there, and we can write in 0.1587. Perfect. Let's do a different color, this nice blue color for this one. So now we're doing an x value of 210. So plugging in all the numbers right there, type away on your calculator, but you're going to get 10 over 20, which is 1/2 or 0.5. So we're looking for probability that z is less than 0.5. So we'll bring up the z-scores, and 0.50, I suppose, 0.6915. So 0.6915. Perfect. So remember, that represents this value here. Okay, so there's that z-score. This z-score was -1. So now I know that this is the big one, so it's going to go there. And the value was 0.6915. Just double check, right? We got the big z-score subtracts the smaller z-score. So we're clearly on the right path here. Got our nice picture. It all makes sense. We're going to take the z-score of 0.5, which represents the big green area. And we're going to subtract from it the little rainbow area, and we'll be left with the in-between area. So this one I'm not going to try in my head. So 0.6915 subtract 0.1587. Yeah, 0.5328. Right, which seems to agree with my answer. So yeah, pat yourself on the back. Another one. A movie theater manager. Well, movie theaters are probably going to not be a thing anymore. Knows that the number of patrons per movie is normally distributed, great, with a mean of... Is this the same question? Oh, no, it's, sorry, same numbers, different question. Wow, okay. Man, if it confused me, it'll confuse you. So mean of 200, standard deviation of 20, but this time, what is the number of patrons? X. Wow, so we're actually looking for X this time, where 80% are less than X. Huh, what? What the heck's it talking about? Well, here's our normal distribution. And here's the mean of 200. So 80% or less than X. So this is one of those reverse questions where they're giving us the area under the curve, and we can calculate the z value. We can reverse look it up on the table, and we're going to be looking for the corresponding x value. So because it's 80%, and we know the mean represents 50% of the distribution, again, the pictures don't need to be perfect that you draw, but, you know, if they make sense, that'd be good. So we're looking for, well, what's that magic x number that gives us 80% of the distribution? So we can actually find the z value, right? So 80% of the distribution is covered. We can go find that z value by looking up 0.8. So go ahead, go to your z tables, and try to find 0.8. Remember, you won't always find exactly 0.8. You might not. So do your best. So right here, I'm reverse looking up. So I'm actually looking at the percentages here. So here's 79.95%. And here's 0.8023. So what do I expect from you? I expect it that you pick the one that is closest to 0.8. Sometimes you can actually average two values and get exactly the one you're looking for. If that's the case, then that would be ideal. In this case, it's not. So this one is 0.0023 away from 0.8, and this one is 0.0005. So this one is closer. So this is the one I'm going to use. So it's 0.84. 0.84. Don't forget. So that is the corresponding z value. Now, more junk mail. So let's see. We have this formula. Now, I've been very nice to you in general, but also in this case on the formula sheet. Remember that I've actually given you, so here's that z-score formula, and if you ever have to reverse look up the z, I've actually given you the formula solved for x. Save you a little bit of algebra. I probably shouldn't, but there it is. So there it is. You can use this, or you can algebraically solve for x. Okay, so here's the formula. I usually solve it algebraically, so excuse me a moment, because I didn't actually look at it very closely. So it's going to be this. This is the formula from the formula sheet. Now we have all the information we need. So the x value is the z-score, so 0.84 times the standard deviation of 20 plus the mean, which is 200. Now you pop that in on your calculator, and here I go. So you get 216.8. I just want to make sure that in this case you actually put the units in. Okay, so it's the number of patrons. So that is the answer. It says where 80% are less than x. So, my answer key, I didn't round. So you might choose to round up. Now, because it's actually 80% are less than x, we should theoretically round down. Keeping in mind, though, that we did use 79.95, so actually maybe it might be more appropriate to round up. I guess the point is in this question, I really, I would mark this right, as long as you had all the work, and I would mark 217 right as long as you had all the work. So I saw that you had this number, then you rounded, so it's all good. You know what? Let's just be happy. Okay, looks like we got 2 more questions left. Let x be a binomial random variable with n equal 150 and p equals 0.3. Approximate this. Well, yes. What is this? Binomial random variable is the binomial distribution. Okay, and with an n value of 150, if I was going to actually calculate this one out using the binomial formula, the discrete one, right, I would have to do this formula a bunch of times and add them all up. Now, this is pretty clear. It says approximate, so I know that I'm going to do the normal approximation, but you always have to check and make sure that it passes this test, that n times p is greater than 5, and that, what's the other one? That n times 1 minus p is greater than or equal to 5 as well. That's on your formula sheet. Oh my goodness, so much junk mail. This is ridiculous. This never happens. Let's see. Where was I? Yes. So, does this work? Is 150 times 0.3 greater than or equal to that? Well, yeah, the answer is this is 45. So 45 is greater than 5. So that check is passed. Now, is 150 times 0.8 greater than or equal to 5? The answer is yes. Now, you do have to show the actual work. Okay? I've seen people assume, and then they're wrong. Okay? So you actually need to show that work. Like, what is this actual number? Okay? So if that's the case, then we can use this formula that has the continuity correction. Remember that plus or minus 0.5 that's in the notes. There. We can use that formula to approximate an x value of greater than or equal to 50. So let's go for it. Probability that x is greater than or equal to 50 is equal to, now because it's pointing to the right, okay, we got our mean. We're going to find whatever the x value is, wherever it happens to be, probably, well, we have to calculate the mean, actually. Right, the mean is n times p. So the mean is 45, so we're looking for greater than 50. So we're going to be like somewhere over here. This is going to be x equal 50. So because we're greater than or equal to 50, that means we're looking for to the right of that value. Okay? So we're looking for probability that z is going to be greater than whatever number we get in our calculation. Now, we also need to figure out the continuity correction. So what is this x plus or minus 0.5? And that's kind of that tricky mind-bending thing where people lose their minds and don't know whether to go adding the 0.5 or subtracting the 0.5. So because I also lose my mind, by the way, I write down both possibilities. It's either this number or this number. Now, you need to make sure that x is greater than or equal to 50. So that means I am including 50. My continuity correction also must include the number 50. So if I go with this continuity correction and I go x greater than or equal to 50.5, I will not be including the 50. So that is not the continuity correction. I need to do 49.5 to make sure that I include the 50. Oh, there you have it. Talk yourself through it, breathe deep, and you'll get the continuity correction every time. Now, is this a big deal? People they never think about it, but how many marks will you lose on this question if you do the wrong continuity correction? The answer is a lot. Because that's the whole point of the question. You're doing a normal approximation. The normal approximation requires that you use a formula that's almost identical with this one little piece being different. So I'm not testing you really to see if you know how to do the actual Z value calculation. I'm testing to see if you know when to use this and how to use it. So if you don't get the right continuity correction, you're missing a big part of the concept. So you're going to lose not all the marks, but a pretty big chunk of the marks. So keep that in mind. Part of the formula is that the mean is n times p. So I'm just looking at the formula sheet, right? So you're still using right here n times p, and here's your standard deviation n times p, 1 minus p. So we need to find those things. So n times p is here. Standard deviation is n times p times 1 minus p, and it's the square root of that. So n times p is 45. 1 minus p is 0.3, so we're going to go 0.7. And we're going to do the square root of all that stuff. So 45 times 0.7. Get 5.6. Now, how many decimals to keep? Keep, I usually say keep 4. So I'm going to round to 6125. There. So you now have all the numbers you need. So I know that my mean is 45 with my standard deviation of 5.6125. All right, plug it in. I have no idea. Numbers are too complicated. In the numerator, you get 4.5. So I suppose I'll show you all the work. When you actually divide that by 5.6125, you get a Z value of 0.80. No point ever rounding to more than 2 decimals for the Z score, right? Because our tables only go to 2 decimals. So we're going to go find, from up here, the probability that Z is greater than that, because the tables give us the tables give us the area to the left. Okay, so to actually find this, we're going to go 1 minus the probability that Z is less than 0.8. Right? Remember, we're looking for the area to the right. The table gives us the area to the left. Okay? So we got to go 1 minus whatever value we find when we look up the area to the left, and that's how you write it. So let's look it up. 0.8, 0.8, 0.8. 0.807881. So 0.7881. So 1 minus 0.7881. I'm feeling lazy, and I am not going to do that in my head. So I get 0.2119. And there you have it. Answer. So, small question, lots of work, lots of fun. Glad we did it. Let's wrap up here. Last question. Let's see if I can do it. The weight of a product is normally distributed. Hello. That's what we've been doing all along. With a mean of 4 grams. Okay, 4 grams. And a variance. Oh, wow. They gave us the variance. Remember, the variance is a standard deviation squared. So the variance is 0.25, grams squared. So right away, all our formulas use the standard deviation. So all you got to do is do the square root of the variance. And I'll do that right away. And you get 0.5. So just to be really clear, I did the square root of 0.25. And that gives me 0.5. Okay. So what is the probability that a randomly selected unit from a recently manufactured batch weighs no more than 3.5 grams? No more than 3.5 grams. So X, no more. So that means less than or equal to 3.5. Now, because it's less than or equal to, whatever Z score we get, we're going to be looking for Z less than our magic Z score, right? Draw the picture. Every time, draw the picture. It's mandatory. So there's the mean of 4 grams. We're looking for 3.5 grams. All right, so we're looking for that magic Z score. This is the mean. And we're looking for less than, so we're looking for the area to the left. The reason why the picture is nice is because it forces you to think, am I looking to the left? Am I looking to the right? What does it look like? So picture, highly recommended. So we are obviously using the z-score formula once again, and there you have it. So plug in the numbers. X was 3.5, the mean was 4, and the standard deviation was 0.5. Now this is going to give us negative, it's going to give us negative 0.5 divided by 0.5. So same number divided by itself. With a negative in front, you should get -1. So we're looking for probability that z is less than or equal to -1. So go on your table, look up -1.0, so 0.1587. So probability that z is less than -1. I forgot what I said. I think I said 0.1587. And there you have it. Now, because I wrote this statement up here, I don't need to rewrite it down here. So that is the answer. And you are done. You're amazing. You did it. You did all those questions. Very good. Don't forget, please don't forget, some reminders. They're the same every week. Do your homework, guys. Email me to ask me questions. Blank nothing. Just a blank thing here. And then check Moodle for updates and check email for other updates as well. So very important that you do the homework. Make sure that you are going through my notes. I understand that it's a video that's usually anywhere between an hour and a half, usually more towards the hour and a half mark. Remember, we have a 3-hour class. So the reason why my lecture gets condensed down to an hour and a half is because there's no questions. Okay, so that's why I make these wonderful videos, and that's why we have our question time together on Moodle as well, and I post those also for viewing. So very nice to see you guys, and you know what? I have a feeling that I'm going to see you guys next time. Bye-bye.